The fourth part of the lecture is dedicated to extremal stresses and special stress states. Getting back to our mitral valve case, we noted that for design purpose, it's useful to find the direction of element perpendicular to the local stress vectors. Now it's beneficial to find the maximum normal and shear stresses on one element, because sometimes the yield and ultimate breakage limit of a material depends on these extremal stress values. Let's see how to find the external stress values. To find the max or minimum stress values, we do it based on the principal stresses sigma star and in the principal frame E star. You see that the x1, x2, x3 Cartesian coordinate is slightly rotated to be aligned with E star principal frame. Here for point P, this plane, we assume it is a principal stress plane. So the traction vector at point P is parallel with the plane normal vector, which is E2 star at this case. Now consider this traction vector, but we want to find its components on a plane normal with a normal vector n. This plane is slightly rotated with respect to our principal stress plane. We want to find the inclination angle of this plane so that the shear component of stress on this plane becomes minimum or maximum. To do that, we use Cauchy stress equation. So the components of traction vector on the plane with normal n is the normal vector dot the stress tensor, which in our case is the principal stress tensor sigma star. So it is basically sigma star, sigma 1, sigma 2, and sigma 3. Now let's find the normal sigma n and shear sigma s components on our plane, our new plane. You see them here. The shear component and normal component of the traction vector on the plane with normal n. We know sigma n is the traction vector on the plane normal to n dot the normal vector of the plane, which in this case becomes sigma, the first principal stress, sigma 1 and 1 square plus the second principal stress and 2 square plus the third principal stress and 3 square. For the shear component, we have our trigonometric relation. So sigma s square is t dot t minus sigma n square, which gives us this equation. Note that we have sigma 1 square and 1 square, and the same for sigma 2 and sigma 3 here, minus bracket sigma 1 and 1 square plus sigma 2 and 2 square plus sigma 3 and 3 square, the whole thing with another square to the power of 2 basically. Also, we know that the norm or the length of the normal vector is 1. So we can find the third, one of the components based on the other two. Here we find the third component of the normal vector based on the first two components. So n3 squared becomes 1 minus n1 squared minus n2 squared. To find the maximum and minimum values of sigma s, which we've already found this equation for, we need to differentiate it with respect to either n1 or n2, and we already know that we can find n3 based on the other two, to 0. So by forming these equations and setting them to 0, we can find 4 set of solutions for n1 and n2, and subsequently find n3 base of them. First, n1 and n2 should be 0. Then we have the case that n1 is 0, n2 and n3 are equal. Then a case that n2 is 0, and then a case that n3 is 0. Let's find the solution for sigma s, this shear component, for each of these cases that are the extremums of our equation for sigma s. In the case that n1 and n2 are 0, n3 becomes 1 from our relation between n3 and n1 and n2. Replacing that in this equation, we get sigma s squared is equal to the third principal component to the power of 2 multiplied by n3 squared, which is 1 in this case, 1 to the power of 2, minus the result for the terms inside the bracket, which is sigma 3, 1 to the power of 2, the whole thing to the power of 2. You can easily see that these parts are 1 and these parts are equal, so the result is 0. For the other cases, it's almost similar. So let's find the solution for the case that sigma 2 and n2 is 0, so n1 and n3 becomes plus minus 1 over a square root of 2. Replacing the equations, replacing n1, n2, and n3 in this equation, we get sigma 1 squared divided by 2 plus sigma 3 squared divided by 2 minus bracket sigma 1 divided by 2 plus sigma 3 divided by 2 to the power of 2. If we solve this part, we get basically sigma 1 squared plus sigma 3 squared divided by 4 minus sigma 1 sigma 3 divided by 2, which is basically the expanded form of this bracket sigma 3 minus sigma 1 to the power of 2 divided by 4. This is equal to sigma s squared, so we can easily see that sigma s itself is half of sigma 3 minus sigma 1. We already know that sigma 1 is more than sigma 2 more than sigma 3 when the reference frame is aligned with the principal frame. So from these, between these three cases, sigma 3 minus sigma 1 is the maximum. So it gives, we easily see that for this case we have sigma s maximum. And also for the case that sigma s is 0, That's the minimum value for sigma s, and in that case sigma n is equal to the third principal stress, normal stress. Basically, in a plane which is a principal stress plane, the only stress vector available is the normal stress, and the shear is 0, so we have the minimum shear. And in a plane inclined 45 degrees with respect to the principal stress plane, we get the shear component becomes maximum, equal to half of sigma 3 minus sigma 1. Half of the maximum principal stress minus the minimum principal stress value, written in this sentence here. Now let's practice it in an example. Given the stress tensor at point P, 9, 12, 0, 12 minus 9, 0, 0, 0, 5, find the minimum and the maximum values for the shear component at this point. This is similar to the stress tensor given in one of the examples in the previous section. So we already know that the minimum shear component is 0. For the maximum shear component, it's half of the first principal stress minus the third principal stress value. We already know from example 3.3.2 in the last section that sigma 1 is 15, sigma 2 is 5, and sigma 3 is minus 15 Pascal. And we already know that the maximum shear value is half of sigma 1 minus sigma 3, which becomes 15 plus 15, and divided by 2, it's 15 Pascal. That's the maximum shear stress we get. We can use this information for design analysis, because some material fail under maximum shear stress, so we need to find this value, and we need to find this direction because they basically break in that direction, like ductile material. But some material break under normal stress, so we need to find the principal stress values and the principal stress planes, because that's basically the value that the material breaks, and that's the principal stress plane is the plane that the breakage happens. Now let's see some special cases. We have for stresses. We have a spherical and deviatoric stress states. When all three principal stresses are equal, we get sigma ij is equal to basically sigma ij sigma m, and we already know the mean value for sigma. We define it as 1/3 of the trace. So basically the stress tensor takes this form, a diagonal 2 by 2 matrix with with equal values for the diagonal element sigma m, and all the other values to become 0. That's for example happens in a fluid at rest. In this case, principal stress is equal and opposite the static pressure of the fluid. So like sigma m is equal to minus P0, the static pressure of the fluid at rest. And you can see it here. So for a specific point, all the principal stress values are equal and there is no shear component on any of the planes. But it gives us interesting results. For example, we can decompose every stress tensor to a spherical stress tensor and another component, the remaining of the stress tensor, which we call it a deviatoric stress tensor. This is how we do it. So basically, the stress tensor is equal to S, a deviatoric part, and a spherical part, which you can show by delta ij sigma m. The delta ij sigma m part is simply 1/3 of delta ij sigma kk. And the deviatoric stress part is simply the stress tensor minus the spherical part, which gives us this. The off-diagonal elements for the deviatoric tensor is similar to the original stress tensor, but the diagonal terms, we just subtract sigma m from the diagonal elements of the original stress tensor. The spherical component controls the body expansion or shrinkage because it's symmetric, and the deviatoric component controls the body distortion because it basically you basically get the shear stresses working in this case. That's basically the importance of doing this decomposition, and also identifying the stress states being spherical, deviatoric, or a mix of them. If the stress state is spherical, you don't have any distortion in the material, which might be desirable for some applications. But if you have only a deviatoric stress tensor, you don't get any body expansion or shrinkage, but you get some distortion of the body. We can define the same decomposition for the infinitesimal strain case as well, or in general strain case as well. Assume the strain tensor epsilon. The spherical strain case is the case that the strain tensor is diagonal, with all of the off-diagonal elements to be 0, and all the diagonal elements becomes all the diagonal elements are equal to 1/3 of the trace of the original strain tensor. We also can decompose a general strain to a spherical one, which basically shows the shrinkage or expansion, a symmetric shrinkage or expansion, and a deviatoric part, which explains the distortion, but no expansion or shrinkage of the element. The same as the stress tensor case, the strain can be decomposed to the deviatoric part plus delta ij epsilon m, which is the spherical part. And the spherical part can be written as 1/3 of delta ij epsilon kk. As a result, the deviatoric component has similar off-diagonal elements as the original strain tensor, but we subtract the mean strain from the diagonal elements. Here again, the spherical components controls the body expansion and shrinkage, and the deviatoric components reports the body or the element distortion. Let's practice more. Here it asks, show that for a deviatoric stress tensor, the first and second invariants are reduced to a first invariant becoming 0 and second invariant becoming minus half of Sij Sji. And also form the general form for the characteristic equation. The first invariant is the trace, and we already know that for the deviatoric stress tensor, the diagonal elements are equal to sigma I minus 1/3 of delta II sigma kk. Expanding that, we get sigma 1,1 plus sigma 2,2 plus sigma 3,3 minus 3 times 1/3 of the trace again. These threes are cancel each other, and then we have two terms equal but with opposite sign. As a result, the term solution is 0. For the second invariant, we already know that it's half of Sii Sjj minus Sij Sji. Comparing this with the final solution, we identify that this term Sii Sjj should be 0. Let's see if we can find that. We already from the first invariant know that Sii is 0 because, as you see, the first invariant is equal to Sii. So Sii and Sjj both are 0. So simply the second invariant is reduced to minus half of Sij Sji. That's the solution for the first part of the question. We can write it as minus half of the trace of S squared as well. For the second part of the question, we already know that the characteristic equation should look like as this: s to the power of 3 minus the first invariant s squared plus the second invariant s minus the third invariant equal to 0. But we already know that the first invariant is 0, so this term is cancelled, and the characteristic equation is reduced to s to the power of 3 plus the second invariant s minus the third invariant equal to 0. And that's the general characteristic equation form for a deviatoric stress tensor. Here's another example. It says, given the stress tensor at point P to be equal to this, one, decompose it to a spherical and a deviatoric component. Second, find the principal stress values S1, 2, and 3 for the deviatoric stress part. First, let's calculate the mean stress value. It's 1/3 of the trace of the stress tensor. In this case, it's 1/3 of 21 minus 63 plus 42, which is 0. So the spherical part is basically a 0 matrix. And the deviatoric part is equal to the stress tensor itself. So this stress tensor is a deviatoric stress tensor. because basically the spherical part was 0. That's the solution for the first part. For the second part, we need to form the characteristic equation. So let's find the invariants. The first invariant is 0. The second invariant is minus half of trace of the deviatoric part to the power of 2. I've already calculated that. It becomes minus 13,230. The third invariant is the determinant of S, which I've already calculated to be minus 509,355. As a result, the characteristic equation becomes S to the power of 3 minus 13,230 S plus 509,355. And I use MATLAB to solve this equation, which becomes which gives us 3 solutions for the principal stress values. The first principal stress is minus 130.85. The second one is 45.727, and the last one is 85.126 Pascal. Let's review some concepts. We talked about the maximum value for shear stress component. It corresponds to any plane oriented plus minus 45 degrees to the principal stress plane. And its value is half of the third principal stress minus the first principal stress. The mean value for the shear component corresponds to the principal stress plane, and its value is 0. Then we talked about the spherical stress states. It's basically equal to the stress state with all of diagonal elements to be 0 and the diagonal elements to be equal to a mean value. And we notice that every stress tensor can be decomposed to a deviatoric and a spherical component like this. For a deviatoric stress tensor, the invariants are reduced to this form. And finally, the characteristic equation is simplified to this form without the S square term, because the first invariant is 0.